Okay. I guess we'll start thinking. One thing to talk about here that is, again, many people have noticed that the financial markets have been turbulent lately, and I have explained, what I know about the turbulence in the markets. But I also have said I am not a skilled business school professor. Fortunately, there is going to be a presentation by skilled business school professors here about the state of the financial markets. There was an announcement that on Thursday, which I guess is 2 days from now, at 3:45 in the Lamu Lecture Theater, there is going to be some kind of a panel discussion led by 4 business faculty here. And so, if you want to find out, so if there's general interest in what's happening in the markets, I might recommend that. It would be interesting to see what the perspective is and to see how it jives with stuff that we've been talking about in here. Okay? So I encourage people to go to that. I gather it starts, it's about, say, registration is at 3:45, and then the thing starts at 4. You can time your arrival appropriately. Any questions about that or about the turbulence in the markets or anything that's going on now? Yeah.
I wonder, is there any winner in this financial crisis?
Is there a winner in the financial crisis? That's actually a good question. And the answer is relative, fewer than there are losers, certainly. Okay, is for the first answer. Okay, that somehow one way to think about the financial crisis is that the market value of everything that is owned in the world has gone down. Okay, and so somehow there's magically less money than, there's somehow $1.2 trillion less in the United States today in market capitalization than there was yesterday. Okay, and that's, presumably a bad thing. Now, the question you might be asking is, who is making money from this? Okay, and relatively few people, but I suspect some. First of all, certain people were selling short some of the financial companies. When we saw Lehman go out of business and all of these kind of things. There were companies that were betting, hedge funds typically, that were betting aggressively against these, these companies. And so presumably some people made money when these companies went under. But I think most people are having a hard time now. It's not clear that there's a big winner here. Okay, a big, let's say, somebody who's really sitting back and snickering from this. Okay, I mean, some people are if they have their investments right. Some people are doing better relative to other people. So let's say if you had your money in gold this week, okay, you can laugh at other people, but you're probably not a whole lot richer than you were before either. So it's hard to say, but that's I guess the short answer. Now there's some aspects of business where you're interested in like private equity companies, okay, that are interested in buying other companies and trying to do something with. As their shares get beaten, if you have if you have money now, if your money is in something that is cash or something like that, this is a very good time for you in some sense, because other things you might buy might have gotten a lot cheaper, okay? But it's not clear that there's a lot of people like that sitting around, okay? Any questions? Yeah.
There is some rumor saying that the American bond there may be a downgrade of the rating of the American bond. But generally, we think that is not quite possible. So what do you think about it?
Well, again, it's clearly a complicated and messy situation, and rating agencies can rate things as they see them, okay? Now, again, if we believe everything we've said in this class, presumably we believe that the United States government can always pay back everything it says it will pay back because it can print money. On the other hand, other parties may be less happy about receiving that kind of money, okay? And that may cause fewer people wanting to loan money to the United States, and that might lower some of the rating. So bottom line is, it's not a good situation, and hopefully will get cleared up more in the next couple of days. But for the record, I would have voted for the bailout package. No one was asking me, but I would have voted for the bailout package in Congress. Okay. Any questions? Okay, let's talk here about random walk models, because this is actually a, we started talking about this a little bit last class at the end, that there's this idea that somehow financial time series, things like stock prices, okay, can be viewed as being random processes, okay? And one argument for that is that if you look at the way a graph that is produced by typical financial time series, it looks quite similar to time series you can generate with simple random processes, okay? And that would be an argument that maybe one model of what stock prices do is essentially random. And as we discussed last class, there are some fundamental reasons why random movements of prices might... Random here meaning is sort of another word for unpredictable. You know, that if the bailout package yesterday had passed, okay, stock prices would have gone up. Instead of going down 10%, probably would have suddenly gone up. And it didn't fail by that much. Supposedly, one side is claiming that they were offended by a speech somebody gave. And if this person hadn't given this speech, or they hadn't been so sensitive, maybe they would have voted for this. Okay? So these are what we would call unpredictable things. And unpredictable things, you know, can maybe be modeled by, you know, random thing. You know, somehow, what is random? Random means unpredictable. If you think of randomness and unpredictability as being the same thing, okay, then that's a reasonable argument there. And there is a considerable academic argument, which we'll talk more about later in the semester, is that basically markets are efficient, the claim is, and that any, you know, sort of heavily traded stock where you have large numbers of people looking at monitoring these things, somehow all the information that is out there will be folded into the stock price already. Okay, and so what's left from now on is only future events that who knows what will happen. Okay, and that then you know, that then would leave somehow random fluctuations. So we talked about the idea that of using maybe Monte Carlo methods. Monte Carlo is the name of a town where there's a gambling casino. That's where the name comes from. Okay? And gambling, randomness, things like this. So the idea would be for our Monte Carlo type analysis of stock prices might be we build a model to generate random walks with the property that they look like, okay, typical price curves for that stock, okay, that is designed in some way so that the distribution of walks, okay, that is built by our model is somehow supposed to reflect the probability distribution of what the price series is likely to do. If we can build such a model, we can simulate the walk 1,000,000 times, 1,000,000,000 times, however much computing time you want, and gather statistics about what are the price distributions produced by this model. And based on that, you can now make intelligent decisions about what is the probability of some event happening with respect to that stock. Any questions? Okay? Any questions about that? So this is pretty much where I got to last time. Now, I got some complaints from people afterwards, okay, who don't like this random business, okay? This idea that somehow stocks are going to be modeled by random walks seems like a funny idea, seems like a hokey idea, okay? Seems like a kind of weird model. So let me talk a little bit about the philosophy of models a little bit. Because computer scientists maybe don't build models to predict the world as much as, you know, you do other things, okay? But models are useful when they have predictive power, okay? That is somehow what the definition of a model is, okay? And the best models are, in my mind, conceptually simple models that you understand what your model is actually doing, okay? What are the assumptions behind it, okay? And what is it you expect from your model, okay? So one of my favorite models in the world is the model that the Earth is flat. How many people here believe that the Earth is flat? People say yes. How many people say no? Okay, good. We're consistent on this. But the fact that the Earth is flat is a very effective model. Okay? When you bought shoes, did you try to buy shoes with the property that they were curved? Did you check the bottom of your soles to make sure they were curved so that they could fit on the spherical surface of the earth properly? Or did you sort of assume that somehow that the earth is flat? And on the scale that you're working on things, okay, the earth is flat. So over a large scale of phenomena, the fact that the earth is flat is a true and interesting model. And trying to make a more complicated model and factor in the fact that the earth is round. Architects on a building this size probably did not worry about the earth being round. If you're building a suspension bridge that's a mile long, you actually do have to worry about the earth being round. Okay? So what is the interesting point here? Somehow that intelligent people believe that the market is somehow unpredictable, that there is this efficient market, the markets are efficient, and that captures a large level of truth. You may argue, well, maybe not completely, okay? But basically, if we work from the assumption that prices, random walk models give a reasonable model of what is happening, it's a useful model because we can make predictions based on random walk models. It's a useful model because they are simple. Random walk models are simple enough, computer science people like you in the room can program them, okay, and think about them and conceive them, okay? And that they capture interesting phenomena. Again, the idea somehow is if you view the future as somehow being some possible path through reality that is happening, okay, from a space of all possible paths, somehow that is really what we are doing. Our random walk model is sort of coming up with the distribution of all possible futures of the world. Okay? And somehow what reality is doing is picking one of them. Okay? If they're picking one according to our probability distribution, we have modeled something about the world. Any questions about that? Okay? About the philosophy here of modeling this stuff. Okay? So, let's now look at random walk models a little bit. So my plan now is we're going to talk about some of the issues that come up in doing Monte Carlo simulations, generating random numbers, building these random walk models. And then at the end, I'm going to talk a little bit about a random walk model we built for stock prices, how successful it was or was not. Okay, just to give you an idea of how this sort of does connect to the world again. So what is the simplest random walk model? The simplest random walk model I can conceive, okay, is, as we said, a world where you start at some point, and every time you flip a coin, and you either go up one step or down one step, okay? And depending upon whether the coin is heads or tails, that describes some path, okay, that will, some path from where you start as a function of time. Any questions about that? So we're going to say we move up a distance 1 with probability p, and down 1 with a probability 1 minus p. Okay? Now, this is called a binomial random walk, because the number of steps we have, let's say we go through n steps, where are we likely to be? That's really kind of the interesting thing. If we think prices move like this, the really interesting question is, what is the distribution of prices we're going to have sometime in the future? Okay? And the way to think about it is, one way to do it is you could write a program to compute these things. Flip random coins. If, let's say, you're having 100 steps, heads probability is P, is 50, let's say 50%, tails probability is 50%. You could go and simulate a large number of these walks, and where they land, okay, that's going to give us an approximation to the right probability distribution. Is that clear? Now what's interesting about this binomial walk problem is that in fact you actually don't need to do the simulation for this. Why is that? Suppose you want to know what is the probability that you are, let's say, let's say that you are a distance d above 0 after n steps. What is the probability of that? Okay, this can be worked out analytically. It's the probability that we got d more heads than we got tails. Is that right? Because every time we have a head and a tail, they cancel ourselves out. If we're ending up d steps above the line, then we have to have had d heads more than d heads more than tails. Is that right? So the number of heads is going to be equal to, what is it? Okay, we know that heads plus tails equals n, and we know that heads minus d equals tails. Does everybody agree with that? So we can solve for a number of heads and tails. What is the probability that we had exactly a given number of heads and tails? This was given by sort of the binomial distribution. We know that out of our n flips, h of them were heads. So we can choose out of the n flips which h of them were heads. The probability we got exactly that many heads was p to the h. Okay? And the number we probably got that many tails was 1 minus p to the h. Okay, or basically n minus h. Okay? This was now the probability that we got that many more heads than tails. So the interesting thing about this model is in fact that it is a simple enough random walk model. So there actually is a closed form. If all we care about is what is the price distribution at the end, the interesting thing is that there is a closed form formula telling us what that price distribution is. Does that make sense? So for this model, we don't even really have to simulate anything. Okay, the good thing about closed forms, some of that's what later on when we go through some of these pricing things. Some things have closed forms, some things don't. Closed forms are good because you can compute them, okay, and evaluate them without doing a lot of random simulation, and you get the right answer. The bad thing about closed forms is that they only typically hold for very simple properties of very simple processes. You can analytically compute what is the probability that you ended up d steps above the line. If I ask you now to compute what's the probability that you ever got d steps above the line, that at any point you ever actually crossed this, that's actually a harder thing to compute, okay, analytically. And so the argument is that somehow if we have a more complicated process or a more complicated property, we should not necessarily expect closed forms for it. Any questions about that? Okay, so closed forms are good, but they require being smart enough to do the algebra or have someone done it for you. Okay, and being lucky enough that there is a neat formula. Okay, this is what the distribution would look like for random walks. Okay, these binomial random walks with a particular probability. Here I showed what would happen if you had 100 coin flips. The one on the left is a fair coin, and it's counting how many heads did we get. If you notice, the distribution is indeed centered around half of 100, or 50, and it's a nice bell-shaped curve, and again, it's governed by this formula. The one on the right is a binomial distribution for a different coin flip property. Okay, and that shifts it over and stuff like that. Any questions? Okay, so what are the properties of these simple binomial walks? The expected number of heads we would get are n times p. The variance, okay, which is a measure of how uncertain is it that we hit the mean, turns out to be n times p times 1 minus p. The more important interpretation of that, as far as I'm concerned, is how far do you expect after you've done n steps of a random walk, how far is it that you are away from the axis? The most likely single point if you flipped an unbiased coin would be that you ended up right at 0. Same number of heads as same number of tails. Although the probability that you actually end up perfectly even is still relatively small. In general, the variance is on the order of about square root n. Okay, the standard deviation is on the order of square root n. This means that you're likely to be, very strongly likely to be, within some constant times square root n of 0. Okay? After you do n such flips. Any questions? Okay? So this sort of, the variance is really what's sort of governing somehow the shape of this probability distribution. Okay? And the argument should be that if you do one of these random walks, realize that the expectation would be 0. But just because the expectation is 0 does not mean the answer is going to be 0. The answer is going to be something around 0, typically plus or minus some constant times square root n. Any questions about that? So let's think of other variants of this random walk model that we can build. Okay, or the simplest thing to realize is that the walk that we just talked about, the binomial random walk, was what we would call an additive walk. Why was it an additive walk? You started, the value at time t was equal to the value at time t minus 1 plus the additive step. What was that last step? Up or down? Right? In the binomial walk, we chose that as being one step up or one step down. But there's no reason why we have to choose it like that. Perhaps we could view it as, if we think of, let's say, as a daily price stream. Does each day do you move up or down by 1? The answer is probably not, right? But perhaps you move up or down by an amount that is governed by some kind of a distribution. So you might pick, let's say, some kind of a normal distribution. Okay, a bell-shaped curve, centered around 0. And let your movement each day be a real amount, okay, drawn from some normal distribution. Okay? That would be an alternate random walk model that has the property that it gets us into continuous prices. Any questions about that? So the thing that I'm trying to now get to you idea is that you can build more complicated random walk models than just this simple thing where steps go up and down by 1. Okay? And the more sophistication, the more complexity you add to your model, perhaps the better it will model what real price distributions are doing. Okay? Any questions? Here's one question. If you want to model, let's say, the year-to-year price distribution of Google or any other stock, would a random walk where, like the ones we've talked about so far, the probability of going up is the same as the probability of going down, and the step size is also symmetric, what is the expected position where we will be at n years from now? Okay? If we have equal up probability and down probability, and our step sizes are also symmetric, where are we going to be? Same place. Is that a realistic model of what we expect stocks to do? Why not? Okay. What? Well, right, because basically if we really had a model where we expected that stocks were not going to appreciate at all, presumably no one would be really betting in stocks, right? So there is, presumably, if you want to build a stock model price, stock price model, one phenomenon you need to factor in is that the random walk, the expectation of what we want our walk to do, should not be to stay centered around 0. Does that make sense? So how can we go about modifying our random walk model so that there is expected to be some upward drift? There are a couple of different ways we could do it. How might we do it? Okay. One way I could do it would be that if I said that the probability of going up is greater than the probability of going down, there would be some kind of drift. Does everybody see that? And that might be one way to capture that in a model. Okay? Another way to capture it in a model is to, if we have something like this thing, model it by actually adding an increasing term essentially at every step. So if we said that the price at time t is the price at time t minus 1 plus some random factor, which is 8t, plus a constant representing our expected amount that we want it to grow. Okay? That would have the property of causing the walk to, on average, drift up. Right? Okay? It's the equivalent, I guess, of having, here you were doing it basically by saying that, proposing that the probabilities of going up and down would change. The other argument is that maybe we change how much we go up or how much we go down on a movement. And that's really what we're doing here with the drifting. Okay? Any questions? This might be slightly preferable because it's probably easier to quantify the effect of the drift. Okay? But there's some taste there. Any question about that? Okay? So these are what we call additive walks, and they give us some flexibility to model these things. Any questions? Another model that's actually probably better for us if we're really modeling price series would be a multiplicative walk. What if, let's say, I have say that the price at time t is the price at times t minus 1 multiplied by my random variable. Okay? Now, let's say that if we think about the discrete case, maybe I multiply it by some constant c when I have an upward movement, and I multiply it by 1 over c when I have a downward movement. What's interesting about multiplying it by either c or 1 over c? Okay? Why do we choose those values as being, let's say, the two choices? That's an up and that's a down. What's interesting there? If we have an up movement followed by a down movement, what happens to the original price? It's unchanged. Does everybody agree with that? The order doesn't matter. Okay? So in some sense, the advantage of this property looks a lot like my additive walk, in that upward and downward movements cancel out. But why might multiplication be a better way to think about price changes rather than additive changes? Okay, this is a little subtle here. If, let's say, we're talking here about a walk where, let's say that an upward step, let's say it was one of these binomial things, where we go up by $1 if we have an upward movement, and down by $1 if we have a downward movement. What happens if the stock is General Motors, which is probably now worth about $10 a share, versus Google, which is now, let's say, at $500 a share? Right? Does everybody see that normally we talk about returns here in terms of percentages of income, right? They talked about the stock price. The interesting notion when the stock went down yesterday was that it went down by 9%. Okay? as opposed to sort of being a fixed additive number. Okay? Because usually we are used to movements as happening in terms of percentages rather than fixed amounts. Okay? Is that clear? So when we build these things, somehow the problem is that if we picture a walk with drift, we sort of believe that the numbers themselves are going to get higher with time, right? We agree that sort of a natural model of this thing is that the prices should increase on average. If we have a fixed dollar amount that we're going up or down at each movement, it will become less significant as time goes by. Okay? Which certainly doesn't make sense in modeling time series. Better instead, maybe we think of the movement as being, we multiply it by, 1.1 on an upward movement and multiply it by 0.99 on a downward movement. Okay? The division of these cancel out. Any questions about that? Okay, so additive walks are not really a good idea is the important point. Okay? We're usually going to think about multiplicative walks or equivalently additive walks on logarithmic prices. Okay, we're going to start hearing the word logarithms coming in at some point on prices. Okay? Note that if we have a multiplicative time series, Vt equals At times Vt minus 1, that implies that the log of Vt is the log of this multiplicative factor plus the log of the previous price. So we can either think about multiplicative models that model percentages or additive models in terms of logs prices. Okay? And that is something we're going to be thinking about a little bit later on. Okay? Any questions? The important principle here to see is that if we had an additive model like the binomial model, that doesn't make any sense in a world where there is drift. Okay? Whereas the multiplicative model does. Okay? And the logarithmic model, the additive model for the logarithmic prices do. Any questions about that? Okay? So it should be clear these are materials you can build random walks from. Now, why might random walk models be a bad thing? Okay, or why might you not like them? Okay? One reason maybe is that if you believe that somehow there is a deterministic reason for everything, okay, this bothers you. Okay? If you believe in technical analysis of prices, okay, some people believe that if you take a look at the curve so far, you can look at that and say, well, that's a double hairnet move or something like this. I can now predict that tomorrow is more likely to be up than down. That is not something that would be modeled by true if prices were modeled by our random walk model, right? In our random walk model, the next price is drawn independently, basically from the last position, right? So, if you believe very much in technical analysis, then this might get you suspicious about my random walk models. I will tell you I trust my random walk models far more than I trust technical analysis, okay? So this does not bother me, okay? But that's something to keep in mind. A bigger problem with random walk models, like the ones that we've talked about, is actually that they don't predict big event changes as much as seems to happen in real life. So let's take a look at our random distribution. Let's say that this here is what we picture as the movement of the price distribution that should result from a random walk model. Okay? The truth is that financial prices have the property that quite often, usually, they are fit by a nice model like that. But occasionally there are days like yesterday. What happened yesterday? There was a big drop, right? And if you look at it, it turns out that empirically, the probability of big drops, or to a lesser extent, big increases, turns out to be more frequent than you would get with typical random walk models. Okay? This is actually a bigger criticism of it. Okay? Is that, that these distributions tend to underestimate the frequency of extreme events. Okay? But nonetheless, they are very useful models. Okay? They will give us some idea of what the price distributions are for option pricing and for lots of different things. Okay? But when you hear people complain about these kind of models or complain about modeling prices, you usually hear them mumble something about fat tails. And what does that mean? If you look at the price distribution, let's say this is the price distribution predicted by our model, the changes that will happen a few days, a year from now. We say that the price is likely to be something like this. Empirically, what seems to be the case is that the distribution of real prices basically is pretty similar to that, except that the probability of large events, okay, is larger observed than tends to be seen in the models. Okay? Any questions about that? Okay? So this is actually the biggest, let's say, caveat about the models that we're going to be talking about here. Okay? Is that they tend to underestimate these extreme events. Any questions? Okay? But like I say, these are useful models. Now why? Any questions at this point? So why are random walk models useful? Let's think now about what we might be able to use the idea of modeling prices by a random walk for. The main thing is what we talked about so far, is that if I have a random walk model that for a particular, for stocks, a stock will give me an accurate probability distribution of where it will be t units of time from now, this is going to be very, very useful. It is all that I really need to price options from what we've talked about, right? Before you had a value, you had this notion of there was an option, maybe this was your option, and it was going to pay off at that price, right? To figure out really what the value of this is, you need to know what's the probability that the price at the end of the period is going to hit, okay, every one of those points. And that is exactly what the output of one of these models is. In principle, it is a probability distribution of the prices somewhere down the line. Okay? I know what you guys really want from your model is not the probability it will go up or down. You want to know exactly what the price will be then. And that I can't tell you. But these models can tell me what is the probability distribution of each price. It can't tell me if it's going up or down. But it can tell me how likely is each price. And that is exactly what I needed to know to price options. Okay? Any questions about that? Okay? So that is why this is a useful thing and how it connects to the whole business. The other thing, though, is to recognize that you can also use these to compute more interesting, complicated events. And my favorite example has to do with bankruptcy prediction. Let's take a look at this thing now. Suppose, let's pick your favorite company. Who's got a favorite company? Okay? Pick one. HSBC. What is the probability that HSBC will go bankrupt in the next 10 years? Can we figure out that from some kind of first principle method? Okay? The way I think about it, you can think about it, and where a random walk model starts to become interesting, is that right now there is an HSBC stock price, right? Now, the stock price of HSBC times the number of shares is the amount of capital that the company is worth. Does everybody think about how much money would it take for me to buy HSBC? Maybe less than it was yesterday. Okay? But basically it would be the number of shares times the share price, right? So equivalently, we could think of the random walk on the stock price as being a random walk on the market capitalization. Does that make sense? The value of the company is going up or down according to some random walk model. When is it that HSBC will go bankrupt? Okay, what is the event that it means to go bankrupt? Okay, it could be when the stock price is worth 0, but more to be precisely, it's sort of when the value of what the company is worth is less than all the debt that it owes. Okay, so HSBC has a certain amount of debt outstanding. Okay, they have borrowed money from other parties, right? They have, maybe they bought a building or something like that. So there is a certain amount of debt that the company owes, right? And the company itself only has positive value so long as it stays above the amount of debt that it has. The moment the market capitalization is worth less than the debt, why should there be an HSBC? Why would you want to own HSBC? Okay? Then it should basically, it has no worth. If you want to figure out when a bank company is going to go bankrupt, suppose we want to figure out what is the probability that HSBC is going to go bankrupt between now and, let's say, 2 years from now. We want to know, of all random walks of its stock price, how many of them dip below the point of bankruptcy? What happens once you dip below the point of bankruptcy? Do you get a chance to go back up? Is Lehman's stock jumping up again? Lehman's dead, right? Once you are dead, you're dead. So in fact, what we really have is a process where there is a barrier. Once you hit the debt barrier, you're dead, right? The probability that HSBC will go bankrupt in the next 2 years, if you have a reasonable price model, okay, has to do with what fraction of random walks will hit that barrier, okay? And of course that barrier need not be smooth like that. Perhaps it's paying off some of its debt now, okay? And maybe that barrier goes down with time. Or maybe they have a, you have a vision of them taking on, they decide they're going to take on more debt here. This debt barrier need not be constant through time, right? It's something that you can model. But once you have a reasonable model of the debt, and once you have a reasonable model of the stock price, you can now compute what is the probability you will go bankrupt. Okay? And this to me is actually an interesting thing. And it's a good example of a parameter that you couldn't compute easily from a closed form. Because a lot depends upon the shape of this debt thing. Okay? And it's the fact that the moment you hit this barrier, you're out of business. So you're counting not the price distribution at the end, but the price distribution of how many walks hit the barrier. Okay? And that's not so easy to deal with analytically. Any questions about this model and why this is a useful thing? I hope people are coming away with the idea that these models are useful, even if they don't tell you if you're going to go up or down. Okay? Any questions? Okay. So, if we're going to go and do these random walk models, we're going to need to use random numbers. Okay, the right way to build these random walk simulations is you need to build them from random numbers. You need some kind of a source of random numbers. And typically, how many people have ever built a simulation using random numbers before? Raise your hands if you've ever built a simulation using random numbers. How many people never built a simulation using random numbers? Okay, I get about half and half. Okay? So, what are random numbers? There are a couple different answers to this question. One thing you could say is, well, I called my random number generator, and random numbers are what comes out of it. Okay? The problem with the idea of random numbers, random is supposed to be unpredictable. In principle, numbers that come out of a program that is running on a deterministic machine is by definition not unpredictable. Okay? If you have a random number generator and you know the current state of the seed, the next value of the seed is completely determined. So there's some philosophical problems that come up in here. Okay? That in principle, to do our simulations, we want really random numbers. But we want them to come from a computer, and so we want a process that's not going to generate random numbers, but generate things that look like random numbers. That's what we mean by pseudo-random numbers. Okay? And by look like random numbers, it means that the distribution of these things has to have the same properties that a random sequence would have. So suppose, let's say, we were going to be picking a random number generator to simulate a coin flip. If we're flipping a real regular coin, what's the expected number of heads after n flips? Okay, half n. Now suppose I give you this random number generator, one that generates the sequence head, tail, head, tail, head, tail, head, tail, dot, dot, dot. This sequence has the property that the expected number of heads is going to be equal to n over 2, exactly what it should be. Does everybody see that? Is this a good random number generator or a bad random number generator? It's bad. Why is it? Well, it's not that it's deterministic, but it's not just that it's deterministic. Okay? Because all of them are deterministic. Okay? The bigger problem is that it doesn't have other properties that we expect with random numbers in it. What's the probability that we're going to get 2 tails in a row? In a, how often should we get 2 tails in a row? By this model, 0. In a real coin flip, maybe that happens half the time or a quarter of the time. It depends upon how you specify what we're looking for, right? But that there are higher order statistics that are not like the randomized sequence, right? If it's really going to be a good random sequence, somehow all of these other properties, the distribution of two character sequences, 3 character, 4 character, dot, 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 should also match what is random. Does that make sense? Okay? In principle, you can measure these things by doing statistical tests. And there are statistical tests that you can do to validate random number generators. But recognize that this is a slippery issue. And that if you did a bad job picking a random number generator, your simulation results would have very little meaning, right? What would your random walk look like if you use the Skiena generator here? Okay? Every price distribution would look like this, right? Okay? And you come out with, an unrealistic model of what the prices distribution is down the line. Okay? Any questions? Okay? So in general, when you read about random number generators, on one level you have to be very, very cautious to make sure that your random number generator is good. On the other hand, if you're using a hopefully decent programming language, hopefully the built-in programming random number generator is reasonably good. One thing to note about random number generators is they all have periods after which they start repeating. In this case, the period was 2. Okay? And in principle, the problem is if you start playing the same random sequence again, that's something that wouldn't happen in a really random sequence, right? So it's important that you not run simulations longer than the period, or else your results start to be less meaningful. Any questions? Okay. So how do you generate random numbers in a computer? Okay? The traditional way to do it, okay, the simplest, old, reliable random number generator is something called a linear congruential generator. Okay? There are more advanced, there are a lot of other ones, but I think it's important to understand at least this thing, to understand how random numbers come from. And basically they're defined by a recurrence like this R of n is equal to some constant times the previous number plus some constant mod some third constant. Okay? So you start out with some initial value, let's say R0, and then everything in the random number generator is set. Okay? Once you have R0, A, C, and M. Any questions about that? Why is it that linear congruential generators should generate random numbers? I argue they generate random numbers for the same reason that roulette wheels generate random numbers. You go to Macau, you can bet on roulette. Does everybody know about roulette? It's this thing where you have this wheel that spins around and there's a ball, right? And there's 36 holes for you to bet on. And the guy starts spinning the wheel and he lets the ball roll around, right? And he starts rolling the ball around. And the ball rolls around and around and around, and it goes clatter, 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 bunk, you lose, right? That's what happens in a roulette wheel, right? So why is that what's happening here? We're taking, okay, what is M? M here is 36. It's the size of the ultimate roulette wheel. A times Rn is a measure of how far are we throwing the ball? How far is the ball traveling? Right? And perhaps the C is telling you where do they start? Where's the guy who's standing there who rolls the ball start rolling it? The idea of both of these things is that if you have a long enough path where you're truncating it and giving the remainder of it, it's very hard to predict which ball it will land in. That is the idea behind both of them, right? So what is the idea? We have A times Rn, a big number times a big number, gives a very big number, plus a big number, mod a big number, but not as big as the very big number, okay, gives us the remainder there. Okay? Any questions here? So this is the idea of a linear congruential generator. Okay? It's important in setting one of these things that you set the constants to be right. What would be a bad value of A? 0 would be a very bad value, right? Because then what would happen if A was 0? What would this generator give you? Same number every time, right? Can everybody see that? What would be what about R1, R0, the first value? Okay? Would that be bad to be 0? Not so bad. It means that the first value is probably going to be C, right? What would be a bad value for M, the remodulus? 1 or something small. Why is that? Because the important thing to see here is that this sequence starts repeating the moment R sub n equals some other earlier value of R. Then the sequence repeats. It's trapped in a repetition loop. Does everybody see that? So you want M to be large enough that the period of the generator is certainly no greater than M. Okay? But might very well be less than that. Okay, if you get unlucky, okay, and hit it. Any questions?
Do we need M to be a prime number?
So do we need M? There then start to be some more complicated number theoretic conditions that are involved here. So my understanding is that M is better off being a prime number. Now why is that? Let's stop and think about this. I think okay, let's say that m is supposed to be I think is better off being a prime number because it tends to avoid certain weirdnesses. You want to make sure that those numbers are used equally often, okay? And there tend to be number theoretic issues that can come up if it's not. But let's see if we can come up with a reason here. So one argument would be, let's look at an example. Suppose, let's say m was an even number, okay? And A, R, and C all came out to be even numbers. We would never get any odd number as our modulus. Is that right? Okay, I believe that I'm right there. Okay? So that's an argument that you wouldn't want an even number. And a prime number is just less even than any other number. Okay? That would be my argument there. Okay? Any questions? So bottom line, this gives you a way of generating random numbers from 0 to m minus 1. Once you have them, you can generate coin flips by testing whether or not the number here is bigger than or less than m over 2. And you can do whatever you want with them. Any questions? Now, there are other games that come up in random number generation, which I think are important for a computer scientist to understand. One thing is, linear congruential generators are very good at generating random uniform numbers in a space between, let's say on an interval. That's really what linear congruential generators were, right? It would generate random numbers on the interval, and if we set the constants right, they'll be pretty evenly spaced. That's good. Sometimes we need random numbers with a different distribution than uniform. And picking random numbers so they are uniformly distributed, or they're distributed with a particular distribution, is a very tricky business. Suppose I ask you now to pick generate a random number uniform in a disk. Here I've got a disk of radius 1. Suppose I want you to pick numbers that are at points that are uniformly selected within this disk. How can I do it? See sort of what the problem is? I'd like to generate points uniformly at random within a disk. How might I go about doing it? Okay? One possibility to note is a point has 2 dimensions. So it's going to be 2 random numbers somehow. That much should be clear. Right? How can I select a point uniformly in a disk? One idea would be to say, well, every point in a disk is defined by an angle. We think about a vector, right? It's defined by an angle which is between 0 and 2 pi, right? And it's defined by a radius which is between 0 and 1. So one possible way I could select a point in a disk is to select an angle uniformly from 0 to 2 pi, right? And then select a radius uniformly from 0 to 1. Does everybody see that that's going to generate a random point in a disk? What's bad about that? That turns out to be a terrible way to generate a random point in a disk. Why is that? Okay? The radius is not, wait a second. Picking the angle uniformly seems fine, right? Because all the points in the disk are equally likely to have any angle. That much I agree with. But do we believe that if we take a look at half the radius, that there are an equal number of points somehow, an equal area in the inner disk of radius 1/2, so much as the donut outside of it? Everybody see that? This method is going to be equally likely to pick a point inside the core of this of 1/2 radius as it is to pick the entire donut, the outer donut, which is going to have a lot more area to it. So if we pick the radius uniformly, what is going to happen? On our circle, we're going to have a lot more points in here than we should, and it's not going to be uniform. Okay? If we were counting on it being uniform for our simulation, this would introduce some kind of a serious error to it. How many people understand what the problem is? See what the problem is. Okay? I want to make sure that's clear. Okay? So how can we get around it? Okay? What is a more reliable way to pick numbers that are uniformly distributed within the disk? Any ideas? Yeah? Okay? So what you're saying is, be smart, okay, and say that, find out what the right distribution is, okay, on this disk, okay? And that if I knew what the right distribution of the radius was, there is a right distribution of the radius, and if I could figure that out, okay, then I could sample according to that. But what's the problem with that idea? You have to be smart enough to know what the Laplacian is, okay? And that is a, that requires sort of a more careful understanding of probability than many people are comfortable with. What is a way to pick a point uniformly in the disk if I'm not that smart? Any ideas? The way that I would do it, as a member of the not that smart crowd, would be what we would call an accept-reject method. What if I were to put my disk in a square, right? Can I pick points uniformly in the square easily? And the answer to this should be yes. How do I do it? If the square goes from 0 to 1, 0 to 1, if I pick up the random values independently, right? Now I can randomly get a point in the square, much of which is occupied by my disk. Does everybody agree with that? So one way that I could generate points uniformly in my disk would be to bound it by something that it is simple to make a prediction, pick uniformly in. And then every time my point is in the square but not in the disk, discard it. Does everybody see that? How often in this case should my point hit the disk? Okay? This is a circle of radius 1/2. This is a box of area 1 by 1, right? You can compute what the area of that circle is. Okay? What is it? Pi r squared? What? Pi over 4. What is pi over 4? That's 3.14159265535 ... over 4. That says 3/4 of the points will be in the circle, right? So this has the property of being correct and relatively simple, although perhaps a little less efficient, because we discard the points that miss, right? Any questions? And if we wanted to do this in higher dimensions, it turns out more points will miss, okay? So eventually it becomes inefficient. If you wanted to find the points within some snake like this, okay, that was very thin, okay, most of your bullets will miss when you shoot it, right? So the good news about an accept-reject method is that it is simple, it is likely to be correct, it is potentially inefficient. Any questions? What about normal numbers? There's a normal distribution, okay? One of the more common distributions we're going to want to sample random numbers from, okay, is a normal distribution, okay, where again we've got a mean and there's a standard deviation given by it, okay. You've all seen in your classes the normal distribution. how can we pick numbers that are uniformly distributed by that? Meaning, in a normal distribution, this is the value, and this is the probability of getting that value. In a uniform distribution, we get each value equally likely. In a normal distribution, we want to get values near the mean more often than uniform values. How can we generate random numbers uniformly? Okay? According to a normal distribution. Okay? Any ideas? How would we use the accept-reject method? What we would do is, if you had a function that could compute what is the probability of getting each value, basically the normal probability distribution, right? You could build a box around this thing, right? You could draw you could take your normal distribution, you could put it in a box, right? You could now pick random numbers in this box uniformly, right? And ask yourself, do they lie underneath the normal curve? Is that right? So long as you compute what is the probability of getting the value of x, okay? It then becomes a simple matter to test whether you are underneath it. Do people get that idea? So one argument is that we could generate normal numbers that way. Okay? The good news is it is simple and you understand it. The bad news is it is inefficient. You may have a lot of numbers that are getting out of this. Is that right? What's another way to look at it? Suppose we now take a look at the cumulative distribution. This is the cumulative probability distribution for the normal numbers, right? What is the probability that I get a value less than or equal to 10 as opposed to 10? There's a formula for the cumulative distribution as well. If I can compute that, what's interesting is if I compute it and then turn my head to the side, okay, I end up what happens if you take this cumulative distribution and instead of looking at it face on, look at it sideways. What you get over here is an inverse cumulative distribution. What does that mean? This is the value, which is what was on this index, right? 5, 10. This is the mean was 10. This is the probability between 0 and 1. So what does this measure? This says that we now know if this is a cumulative distribution. The cumulative distribution tells us what is the probability we were less than or equal to something, right? By tilting this thing on the side, we have one dimension that goes from 0 to 1, which is a probability, a uniform probability. And the other dimension is the value, right? These are the normally distributed numbers that we want to get. If we pick a uniform random number between 0 and 1, we can then look up what was the corresponding value at that level of the inverse probability distribution. And what's neat about this is it gives us a way to look up from just one number, just one random number, to get a normally distributed thing from it. Look at this particular distribution. This distribution was normally distributed around a mean of 0. Most of the probability space is very close to 0. It is only as we get far from 0 that we get, that at the fringes of our probability, that we get values that are far from 0. By using this inverse cumulative distribution, we can take a randomly distributed real number and map it to a normally distributed number, okay, in one somehow step. How many people see what I'm saying? How many people don't see what I'm saying? Okay, several people. Good. I like that level of authority. Okay? Let's go back and look at it here. Let's think a little bit about what we're trying to do. We want to write a program that will give me a random number back, which is given by a normal distribution. What is given by a normal distribution? The grades I'm going to get at the end of the semester are going to be normally distributed. Right? There's a bell-shaped curve associated with that. There's a formula that you have seen generating the normal distribution. And it has the property that it is centered around the mean. The mean is the highest probability thing. And that it diminishes in this bell-shaped way, in a way parameterized solely by the mean and the standard deviation. That was what the normal distribution was. And if we wanted to pick numbers according to the normal distribution given in blue, it would be the case that we would want our numbers, more likely we get a number near the mean than far from the mean. And that the probability of getting one farther from the mean diminishes according to exactly this probability distribution. So how do I propose to generate those normally distributed numbers? Let's look at the cumulative distribution function. What is the cumulative distribution function? It's what happens if you integrate over the probability distribution. As you move up, it's the question of the summing up all the probability as we sweep to the end. If this is a probability distribution on these numbers, when we consider the greatest possibility, the probability that we get a value less than or equal to infinity is 1. That's what the cumulative distribution here is saying, right? The probability of getting a very small number is very small. The probability of getting something less than a very big number is extremely large. And the fact that there is this steep ramp up in the middle means that over this range is where most of the probability space is. That most of the time we're going to want to return a number within one standard deviation of the mean. So how will we do that? This is the cumulative distribution function. Note that it maps our values to probabilities. What is the inverse cumulative distribution? If this maps numbers to probabilities, the inverse distribution function maps probabilities to numbers. And that's exactly what we want to do for generating normal numbers, right? This maps probabilities from 0 to 1. This maps probabilities from 0 to 1, right? But we know how to generate uniform numbers, okay, by using our linear congruential generator. The inverse distribution says that if we pick a number anywhere between 0 and 1, we can map to what is the probability that caused that. Okay? And this gives us a mapping then between uniform numbers and normal numbers. Okay? If our distribution was a straight line here, we would be mapping uniform numbers to uniform numbers. But because there is this bump here, okay, we can generate it according to any distribution where we have the inverse cumulative distribution. Any questions about that? I don't know if that made it any clearer or not. Okay? But the idea here is somehow that, again, there are ways of generating these things. And in fact,
There are even more clever ways of generating these things. There's a whole literature on generating random numbers according to specific quantities, properties. Okay? That is very interesting. I don't want to go through the details of it. But sort of like was being suggested there, if you're smart enough to know how to weight these things, you can perhaps generate these numbers, okay, in a way, okay, without, that basically involves just basically doing a transformation to independent, uniformly generated numbers. Any questions? Okay? I'm not going to go through the details there. So there are lots of properties that can happen that we would like to be able to deal with when we're generating random sequences. The last one I'm going to talk about today is this idea of generating correlated sequences. Okay? Now suppose, let's say, we wanted to generate as a reality, let's say, the price distribution of all the stocks on the market. Okay? As one, let's say I want to predict what's going to happen to the S&P 500, right? What's the probability distribution of changes to the S&P 500 after a certain amount of time? We could have done a random walk on Google, and a random walk on Yahoo, and a random walk on Microsoft, and a random walk on Lehman, and a random walk on other things, right? And then total things up at the end. But what would be the problem with that? Why might that not be a very accurate model of what's going to happen to the S&P 500 if we do independent walks for each of the stocks and average that out? The magic word was independent, right? Yesterday, market dumped 9%. Did any of these stocks go up? Probably not. I haven't looked at it, but I imagine it was a bad day for everybody, right? And the reason is because there's correlations. Okay? There's logical correlations between companies. When it looks like the world is melting down, everybody is going to do badly except the firemen, I guess. Okay? So you would expect that their movements are going to be correlated. And if we want to model this kind of thing, we need a way to generate random sequences with the property that they are correlated. The right thing that we would want to do is to figure out what is a random history of the world, where for every pair of stocks we know what their correlation is. Okay? How can we generate time series with the property that there is still a random component, but you get the observed correlation? Okay? Any questions about that? Do people see what the problem is? That's the first thing. Is that right now we have a natural way of generating independent time series, but to make them correlated, there is an interesting transformation. Okay? Suppose I've got that x1 and x2 are two uncorrelated time series. Okay? Independently generated time series. These you can do relatively easily, right? How can we make two randomly correlated, random but still correlated time series? The argument is this. Define a new series, x1, as being the correlation rho times x1 plus the square root of 1 minus p squared times the other correlated independent sequence. What's interesting about this? What is the value of a correlation coefficient when two sequences are uncorrelated? What is the value of the correlation for that? 0. What happens if you plug in 0? You get 0 times plus 1 minus 0 squared. If you have rho is 0, then in fact y2, 1 is going to be exactly x2, right? And you end up getting two independent sequences. What is the most correlated sequences can be? 1. That means that the other one is completely determined by it. Well, 1 times x1 plus 0 times x2, it would give us that one. Does everybody see that? So what's interesting here is, and what if, I guess the other possibility is minus 1 if you're negatively correlated, right? And then it would be negative x1. Okay? Bottom line, this is the right transformation. And enables us to sort of take a distribution, okay, where these are both independent, and skew them so they have arbitrary correlations. Okay? Any questions? And as we should be able to see from this, it's a sensible model for modeling correlated sequences. And there is a generalization of this beyond 2 sequences. So we can generate random sequences which are correlated. Okay? Any questions? Okay, I'm going to leave at this point, but any questions about this random modeling? Next class, we're going to look a little bit more about some of these random generation issues before looking at a model for how you generate stock prices randomly, okay, using these kind of random walks, and then start to get into more powerful methods for these kinds of things, okay? That start to maybe a little bit more principled, okay, like binomial trees. Any questions? Thanks for your attention. Talk to you guys next time.